Okay, so binders. I split that score up into two parts. So one was completeness, which was mostly just like, did you do the homework? Although I think there probably were a couple of people, if I remember, that the notes were pretty sparse. And so, whoops, completeness. So, you know, I might have taken a point out for that. But yeah, that was mostly just homework, doing every problem of every assignment. There were a lot of people that, at least I didn't see the outline that was assigned. So if you look through it and somewhere there's a thing that says outline question mark or missing outline or something, and I just didn't see it, then come talk to me and I'll fix that. There also were a lot of people who didn't have the, we're going to do all these problems 2 times. And to me, that's an important part of learning this material. And so that, you know, there were a handful of people, a lot more than one, who didn't have the second time doing the intro problems, the even numbers of the intro problems. So I took points off for that too. If I missed that somewhere, come talk to me. And then the second one was, I think I wrote it as clarity and legibility. So here are the things that I was looking for with that. I'm looking for careful figures. When you draw figures, they should be drawn, you know, with some effort to like make parallel things look parallel, perpendicular things look perpendicular, make it clear what direction arrows are going. On the homework assignments, you know, it should be written pretty clearly. I mean, these are habits that you need to get into now because other people are going to have to read your work when you're working, and I guess all through school too. I was more lenient on the legibility with the notes because I know you're just trying to get stuff written down as I write it down. But so legibility, I was mostly looking at the homework problems, but yes. Yes. Yep. If you just put those notes in there, that's fine with me. But you should read them or watch the video or something or be in class. That's my recommendation. I can't enforce that, but yeah, you know, I'm expecting that this binder is going to be your main source of information going back later when you want to figure this stuff out. And so I was sort of asking myself as I went through the notes, would I be able to, you know, could a person reasonably be expected to follow the stuff that's in here? And if stuff's just all over the place, you know, the sentences aren't complete, there's a word here and arrows, like, it's just not going to be any use to you. So I was pretty lenient with the legibility, but that's sort of what the clarity referred to. Like, could you go back and use this as a reference? And I will say, you know, that the few people who are doing the best in the class, by pure happenstance, had the clearest, most legible notes. You know, it's not, it's a good habit to get into. I mean, if your notes are organized, your thoughts are organized in your head, you know, that's not always the case, but it's often the case, you know. right now, does anyone have any questions about the binders? Okay. And then the exam, the average was about 85. The median was a little bit higher, let's say 89. There were half of the class had scores above 89% and half below. Yep.
If you did your intro like the even odds all on one page, you did that point for that, you went on two separate like evens and odds, or did all even and odds?
Well, so there should have been the first time you did it that was all of them, and then the second time you did it was evens. And I don't care if that's on the same paper, but you know, you should have the odds once and the evens twice. So I've been doing that recently with problems, and so far I like it. Just having you go back later, do the problems again. You're going to go back later and do the odd ones. It's just so that, you know, in your brain, like I did a problem like this, and I know I did because I did it on two separate occasions. That's the idea. Any other questions? Are there any exam questions you'd like to see me go through? Yeah. Oh, that's the one where you have to interpolate. So you have a saturated water vapor in a fixed tank. With a volume of 0.5 meters cubed. And it has an initial pressure P1 of 0.35 bar. Heat is added until the pressure P2. So we're doing this by putting energy into it through heat. And pressure 2 is 0.6 bar. And the temperature at the second state is 236 degrees Celsius. And we're going to do this with a table. So first, what's the mass of the water vapor? Second, what's the initial internal energy? And it's not asking for a specific internal energy, it's asking for the actual internal energy. Then have to interpolate to find the internal energy at state 2. And then finally, what's the amount of energy transferred through heat? So what's Q? Okay, so for the mass, we can use either one of these states. Well, here's the idea for A. The specific volume is equal to the total volume over the mass. And so the mass is equal to volume over the specific volume. And so if we can get that specific volume from the table, we can calculate the mass. So first, for saturated water, it's on the same table. So we're, let's see, at state 1, we have a pressure of 0.35 bar, and that happens to be one of the blocks of data on this table. And the temperature is the saturation temperature. So P1 is 0.35 bar. The temperature is the saturation there, which is 72.69 degrees Celsius. And if you use those to look up the specific volume, you get that V1 is equal to 4.526 meters cubed per kilogram. And so the mass is equal to, it's a fixed tank with a volume of 0.5 meters cubed. So that's 0.5 divided by 4.526. And you get M is equal to 0.1105 kilograms. And then for part B, the initial internal energy, well, you can just look up the specific internal energy. That's equal to 2473.0 kilojoules per kilogram. And now we know the mass, so the total internal energy is 2473.0 times 0.1105. And could someone multiply that out for me? Oh, I have that here. 273.27. That is in kilojoules. Now we want to find the internal energy at the end. So we're going to interpolate. So we want to find the internal energy. We're going to find the specific internal energy as a function of, well, we want to find it at the pressure of 0.6 and a temperature of 236 degrees Celsius. Okay, so what do we have? We have pressures of 0.35 and 0.70 bar. And we have temperatures of 200 and 240. So the internal energy at, so I'm going to set it up like this. So at 0.35 bar and 200 degrees Celsius. We have an internal energy, specific internal energy of, so this is 0.35 and 200, and the specific internal energy is 2660. Up here, this is 0.35, 240 degrees Celsius, and that's 2720.3. This is all kilojoules per kilogram. Over here we have 0.70, 240. That's 2719.3. And then the last one is at 0.70, 200. And that's 2659.1. And so I'm going to first interpolate to find, so first I'll get U at 0.6 bar and 200 degrees. That's going to be equal to 2660.4 plus the quantity 2659.1 minus 2660.4 divided by 0.70 minus 0.35. And then our delta P, our delta pressure, going from the starting point of 0.35 bar is going to be 0.25. $2659.5. Okay. And U at 0.6240 is 2720.3 plus the quantity 2719.3 minus 2720.3 divided by 0.70 minus 0.35 times 0.25. What do you get for that one? 2720.3. Now we're going to use these two to interpolate to a temperature of 236 degrees. So U of 0.6 bar, 236 degrees Celsius is 2659.5 plus the quantity 20, what?
Sorry, I got for the 0.6240, I got 2719.6. Not 2720.
Oh, yeah, I guess it, yeah, that's the same as one of the boundaries. 2719 point, what, 6? So this one's 2719.6 minus 2659.5 divided by 240 minus 200, and then times the change in temperature, which is positive 36. And what do you get for that one? 2713.6. Okay. And this is in kilojoules per kilogram. I wanted the actual internal energy, so the last step is U at state 2 is equal to 2713.6 times the mass of 0.1105. And what do you get for that? $298.67, and that's in kilojoules.
Only doing a single interpolation on this one because it doesn't vary much at all. Still like 26 volts.
If you would have, so if you said something like that, you know, explain that, your thought process, maybe. Probably, I would have been like, wow, I didn't notice that. Smart move or whatever. But, you know, not if you just, I would have just assumed you didn't know you had to do it twice if you didn't say anything, you know. And then the last one is, what's Q? And so we know that the change in internal energy is equal to the heat added minus the work done. There's no work done because this is a fixed tank. There's no electrical work or anything like that, so that goes to 0. And so Q is just equal to the change in internal energy. So Q is also equal to 298.67 kilojoules. Oh, yes. Okay, so that's U2. Yeah, so that's the final internal energy. Delta U is equal to U2 minus U1. And so that's 298.67 minus, what was the first one? Did we calculate that before? Yes. 273.27. And what do you get for that? 25.4 kilojoules. And so Q is equal to 25.4 kilojoules. That's my final. Any questions about that problem? Any other things on the test? Sure. Okay, so number 3, there's gas contained in a closed tank. A resistor inside the tank transfers energy to the gas at a constant rate of 1 kilowatt. So let's say energy is added to the gas, added to the system by work at a rate of 1 kilowatt. So 1 kilojoule per second. Heat transfer from the gas to the surroundings. So energy goes from the gas to the surroundings. In other words, energy is lost from the system by heat at a rate of 0.01 p squared, and that is in watts. And this T is in seconds. And we want to know first, what's the rate of change in internal energy in watts? So what's dE dt watts? And then second, what's the change in internal energy? So this is internal energy. I have that written as total energy, but we don't have any reason to think there's kinetic energy or potential energy. So I'll rate that as internal. And then what's the change in potential energy as a function of time? Okay, so du dt is equal to the rate of heat added minus the rate of work done. Q is, so du dt. Q dot is positive if heat is being added to the system. In our case, it's being subtracted. So this is equal to 0.01 T squared negative. And then work is being added to the system. W dot is positive if the system's doing work. This is negative 1 times 10 to the third. The times 10 to the third is because this is given in kilowatts. And so du dt is equal to 1 times 10 to the third minus 0.01 T squared. So the rate of change of the internal energy is greater as time goes by. And then second, we want to calculate the change in internal energy from time equals 0 to t. If you want to make your math professors happy, use a dummy variable in the integral, but I don't care about that. So delta U is equal to the integral from 0 to t of 1 times 10 to the third minus 0.01 t squared dt. So delta U is equal to 1 times 10 to the third t minus 0.01 over 3 t cubed. Any questions about that? Any other test questions? Okay, then let's do number 1 after that. I've already identified the pattern. Pattern recognition is sort of my thing. Yeah. Okay, so 0.6 kilograms of gas is, yeah. Mm. For A,
Well, he's asking what's the rate.
Yeah. so I could have given a number if I would have given an amount of time. You could have given a number if I'd given an amount of time, but otherwise, it depends on that amount of time. Mhm. Okay, so for number 2, 0.6 kilograms of gas is in a insulated piston cylinder. Um, insulated means Q is 0. It undergoes a constant pressure process. Uh, where P is 5 bar. Specific volume starts at 0.1 meters cubed per kilogram and ends at 0.8 meters cubed per kilogram. 5 kilojoules of electrical work is added. What's the change in internal energy? So let's write out the equation first. The change in internal energy is equal to the heat minus the work. It's insulated, so there's not any Q. And then W is equal to the W due to expansion plus the W from that resistor. And remember, W is positive if work is done on the surroundings by the gas. So if energy is lost to the gas, in this case, energy is being gained by the gas. This is going to be negative, and so this is negative 5 times 10 to the third joules. Sorry, that's this one. Negative 5 times 10 to the third joules. And this one is the integral of PdV, which, since it's a constant pressure process, is just going to be P times V2 minus V1. P is 5 bar, so 500,000. V2 is 0.8 times 0.6. V1 is 0.1 times 0.6. Okay, so what's 500,000 times 0.42? Okay, so 210 times 10 to the third minus 5 times 10 to the third joules. So that's positive 205 times 10 to the third joules. And so delta U is equal to negative 205 times 10 to the third joules. Any questions about that one?
The system is going to work.
Yep. If it expands, the system does work. Yep. If it is compressed, work is done on the system. And then number 1. So it has a circular shape. There's a downward force of 1,000. There's also a downward force of 1 times 10 to the 5th times the area. And then there's an upward force of that internal pressure times the area. The area is pi r squared I don't have that written down. But so you can write this using Newton's second law. So 1 times 10 to the 5th times A plus 1,000 is equal to that internal pressure times A. And if you solve it, you get pressure is equal to 8.958 times 10 to the 5th pascals. Sure.
How did you get a final value of negative if your expansion plus your electric is a positive 205?
Yeah, because I'm plugging it back into this equation here, and that work term is negative in that equation. You know, all this stuff would be, the signs and everything would be a lot easier to deal with if they just always called these energy terms positive if work is being added to your system. But we don't get to choose that anymore. So, yeah. Mm-hmm. Yeah, I think there were a lot of people like that. Yeah, 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 yeah. Okay. So that's the test. So let's go back to what we were doing before. We're using the first law of thermodynamics. For control volumes. And the equation looks like the rate of change of energy in the control volume is equal to the rate of heat added to the control volume minus the rate of work done by the control volume plus the rate of mass flow into the inlet times the quantity. So now we have enthalpy at the inlet plus speed squared over 2 plus 9.81 meters per second squared times the height at the inlet minus the rate of mass flow at the exit, out of the exit, times the quantity enthalpy at the exit, plus speed squared over 2. I guess I'll give this one the subscript I and this one the subscript E, plus GZ exit. Okay, so this is the rate of energy coming in at the inlet, all of this stuff together, and this is the rate of energy out at the exit. And I said last time that, so this is the full equation for first law of thermodynamics for a control volume. And then a lot of these things are going to be zero pretty often. So we're never going to deal with anything that looks very much like this. A lot of things are going to cancel. So let's think back about, so stuff will always cancel. Why? Okay, so let's go term by term. First, what about the rate of change of internal or of mechanical energy, all energy, inside the control volume? Why would that cancel? Steady state, yep. So if it's steady state, any properties representing the control volume have to be constant. The rate of change of properties has to be zero. Next, what about the rate of heat added to the control volume? Insulated, yep.
Or
Yep. So moves through fast, that's right. And that's right. Yep, good. That's the one I forgot. Small temperature difference.
Can you tell us if there's a small difference, or would you give us a range and
Yeah, well, I mean, it's just a matter of how much precision you need. I guess, yes, the answer is there'll be stuff in the problem that will tell you that. It'll say ignore this, or it'll say that there's a small temperature difference, or yeah. I'll give you something in the problem to tell you what equation. It's in my interest to have you all use the same form of the equation on problems, so I'll make that clear.
But I guess one thing I do want to clarify is when you say small, it's always going to have to be small relative to something. What's the parameter?
Well, yeah, so, I mean, basically, like, the bigger that temperature difference is, the bigger the rate of heat leaving by conduction through the boundary. Okay, there's no cutoff. It's just It's just a matter of what would that difference be. And for engineering applications, apparently it's frequently, usually the case that there's not enough of a temperature difference for that to come into it. Well, I mean, it still would come in. Actually, one of the examples we're going to do is one where we'll use one of these simplifying approximations, and then we'll actually plug the numbers in and see how much it affects it. It always affects its sum. It's just an order of magnitude thing, you know. Okay, so now, what are the things that affect the rate of work done by the system on the, by the system in the control volume on the surroundings? And one thing about these, do you need all of these to be true, or any one of these is enough? Okay. So any one will do it. So now,
unless it's compensated by another one of them being like if the surface area was small but the temperature difference is like
right, the sun. Yes,
like
right.
That, yeah.
Don't think about it like that. Okay, and now for the rate of change of energy that leaves from work, what are some reasons that this would go to zero? Yep, no displacement at the boundary. What's another one? The one that is sort of seems kind of questionable to call it work. Seems sort of thrown into work for no reason. But that's true, no rotating shafts. So motors and stuff, you wouldn't use this. The one I was trying to get at was electricity.
It's thrown in to call it work.
Yeah, it seems like it to me. Like it seems like it could just be thrown in anywhere. Or heat. I mean, that electrical work is raising the temperature. But I suppose, I guess the idea is that it's actual charged particles that are being moved a distance apart or whatever. So while it's still electricity, it's doing work. But anyways, electrical work, if there's none of that, then the work goes to zero, and that's it. The key thing is, do we need one of these to be true or all of them to be true?
Electrical energy. The electrical thing is that in some sense it doesn't matter all that much how it's categorized.
Right. Exactly. Yep, exactly. It seems like they just had to choose something to throw it into. But, okay, what about kinetic energy? Well, I'll do these. This is usually small compared to the other terms. And this is the one that we're going to get to an example eventually where we make the assumption there's no change in kinetic energy, and then we actually calculate it for a realistic set of values, and we see how small it is. And then potential energy. If the change in height is negligible, then this goes to 0. Most of the time that's going to be the case. We'll do one example in this section where we can't ignore that, and that's for a liquid pump. Like if you're trying to pump water out of your basement, it's a really key thing to know that you have to pump the water 5 meters up, but the other examples, I think all the other examples are going to have that be 0. Okay, so now we get to the first application, nozzles and diffusers.
Earlier on, you said
Yeah. Mm-hmm.
So, but up here you just said kinetic energy is usually smaller compared to other terms. So does that also that you have to say ignore it also for that?
Yeah, it's usually small enough that you can ignore kinetic energy. No, you can get, so we'll see, like with a pump, you don't use a change in kinetic energy to get that change in potential energy. You use change in enthalpy or something between the two. So yeah, we're used to thinking of just mechanical energy as being an exchange of kinetic and potential, but that's only in certain cases, and now we're dealing with other cases where there's other forms of energy. So nozzle and diffuser, I already drew this picture. So if you have something going this way, okay, so here are the two examples. Okay, which of these is a nozzle? This is a diffuser. For the nozzle, so if this is state 1, state 2, state 1, state 2, for the nozzle, which velocity is higher? Yep, so V2 is higher than V1, and which pressure is higher? Yep, 1 is higher than 2. For the diffuser, it's all reversed, so V1 is higher than V2, and P2 is higher than V1. And here are the assumptions that we're going to make. First, we're going to assume that the flow of material, there's no big change in height. So what term is going to go away because of that? Yeah. Yeah, so the change in m dot g z is 0. We're going to assume that there's no accumulation of material inside the control volume. And so this is in steady state. And so what do we know because it's in steady state? Yep. The EDT for the control volume is 0. We're going to assume that there's no displacement at the boundary, no rotating shafts, no electricity. You write all that. W dot is equal to 4? No, 0. Exactly. Yeah, thanks for finishing that. And it's moving through fast. So there's not going to be any heat. So QCV dot is 0. I said before there's no accumulation of mass inside the control volume. So M dot at the inlet is equal to M dot at the exit. We'll just call it M dot. And so what do you get when you put this all together? So we'll start with this. dE dt is equal to Q dot minus W dot plus, I guess I am going to make the switch now to the MI dot and the ME dot. I'm going to call each of those just M dot. So we have the enthalpy at the inlet plus the speed squared at the inlet over 2 plus GZ at the inlet minus M dot times the quantity enthalpy at the exit plus V exit squared over 2 plus GZ exit. Okay, so what goes away? This goes away. This. No change in height. And so we're left with an equation that just comes out to be M dot times the quantity HI plus BI squared over 2 is equal to M dot times the quantity H exit plus B exit squared over 2. And you can keep moving this around a little and come up with this form that says the enthalpy at the well, let's say the enthalpy at the inlet minus enthalpy at the exit is equal to the speed at the exit squared minus the speed at the inlet squared over. I don't know if that's the best form. You can put that in whatever form you want, but those are the terms that matter. So what's going to contribute to the change in speed is the enthalpy at the two ends. Okay, and if you can calculate the enthalpy, you can calculate the speed, or vice versa. So here's an example. So let's say this is a nozzle. And you have steam entering. So it's steam at the inlet. Pressure at the inlet is 40 bar. The temperature at the inlet is 400 degrees Celsius. Speed at the inlet is 10 meters per second. There's no heat transfer. There's no change in potential energy. Okay, so here's a question. If on each individual problem, I'm going to give you the assumptions that you can use. What was the point of going through all of this and coming up with this simplified equation Like if we're going to have to start at the original, at the full first law each time and cancel stuff, what's the point of even giving this? I think to me this is just a nice intuitive thing. This is the rough ideas of a nozzle. If you're trying to figure out what the speed is of the water coming out of a hose or something, you could use this and tables and a couple of assumptions to do a rough calculation in your head. But for the individual problems, we're going to have to make sure that each term cancels before we cancel it. Okay, and then P2, is P2 going to be bigger or smaller? Don't look back. Than P1. So let's say 15 bar. P2, bigger or smaller? Bigger, so let's say that's 665 meters per second. And over the whole thing, the mass flow rate is 2 kilograms per second. Okay, so let's say the first thing we want to know is, could we do this nozzle with our thumb? Could we just use our thumb to make this nozzle? No, probably you don't want to do that with a 400 degree Celsius steam. Okay. So we want to construct some kind of thing. And we want to calculate the exit area. T2, we do not know what that is. We could, so that's, and we're not going to try to find that, but you could then go back and use a table to figure out what it was. So calculate the exit area. That's what we want. Okay, so how do we get the exit? No exit area appears in any of this stuff. How do we get that into the calculation? So remember this, the rate of mass change is equal to the density times the change in volume. And density is 1 over specific volume. So you can write this as A times the speed over the specific volume. The capital V is the speed. Little v is specific volume. And so A2 is equal to, if you rearrange this, m dot times specific volume divided by the speed. This would be at instant 2. Okay, and now plug this into the simplified first law. Let's see. So we have, so let me write it the way I had it before. So we have H1, H inlet minus H exit is equal to the speed at the exit squared minus the speed at the inlet squared over 2. And so now we need to have enough information at one of these to use the table. At instant 1, or at the inlet, We know the temperature. Okay, that the state is vapor. We know the temperature is 400 degrees Celsius. We know the pressure is, what was that? 40 bar. And so you can use the vapor table, and it tells you that H inlet is 3213.6 kilojoules per kilogram. If we had a little more information at the exit, we could just use the table to calculate the enthalpy change there too, but we don't. We have to use this equation. So 3213.6 minus the enthalpy at the exit is equal to the speed at the exit, 665. Oh, and be careful with the units. So this is times 10 to the third. So this, I'm writing this now in joules. 665 squared minus 10 squared divided by 2, and you can use that to calculate that the enthalpy at the exit, specific enthalpy at the exit, is equal to 2992.5 times 10 to the third joules per kilogram. Okay, so now in order to calculate the area at the exit, we know that rate of mass transfer. We know the speed at the exit. We don't know the specific volume. How are we going to get that? Well, now that we have this enthalpy at that state, we can just look through that table for an enthalpy value that looks like that. So go to the table again. And if you have a pressure of 15 bar and an enthalpy of, specific enthalpy of 2992.5 times 10 to the third joules per kilogram, then you can figure out that the specific volume is 0.1627 meters cubed per kilogram. And then finally, A2 is equal to, so we had that as m dot times the speed at 2 divided by the specific volume at 2. You can plug all those in now and you get 4.89 times 10 to the minus fourth meters squared. Any questions about that? Yes. Oh, I wrote it as, thank you. Where did I rearrange that? Yes. specific volume up here, speed down here. Okay, I'll give you a couple problems to do with nozzles and diffusers. The next thing we're going to talk about is turbines. And turbines are used to generate power. A fluid, either a gas or a liquid, flows into these blades and spins a shaft. And the idea is that the gas at the inlet has a high pressure, the gas at the exit has a low pressure. The gas that's used, I think is the case that most of the time it's steam that's used for turbines. And I don't know if you have this impression, but when I think of steam being used in power plants and stuff, I kind of have this image of like an olden day like factory or whatever. Like steam is not like a high tech thing, but in fact, like in turbines, they do use steam. What's high tech is just how they get the steam up to the super high temperature. So, like in a nuclear plant, they use nuclear fission to get this steam to this incredible temperature, and then they still use the steam to turn the turbines that eventually create electrical power. So turbines are coming up next. Oh yeah, no class Thursday, no school Thursday or Friday. A quiz? No, the test is on the 30th. Is that right? That's what I have. That's what I thought I noticed. Let's look. A test next Tuesday? Let's get to the bottom of this one.
We just haven't had a quiz yet.
Yeah, that's what I saw on the solar.
Yeah, let's postpone that one. So, all right, so it will be no earlier than the 31st. Okay, so on Tuesday I'll tell you when it'll be, and you'll have at least a week before. Okay. All right. See ya. Yes. Mm-hmm.